As you can see, we have a distinguished set of panelists to help us better understand the current situation in Poland and the challenges that many district heating companies are facing in their efforts to decarbonize their system. So I strongly recommend you to pay attention, as it will be a very interactive and high-paced session. Marco, would you like to say a couple words about today's session, or your perspective on this first Knowledge Exchange Forum?
So thank you very much, Emilia. I would not take much time. I think you did a perfect introduction about the project, and I warmly thank you for this nice icebreaker. I'm also very glad to have our panelists with us today. Some of them are directly part of the HeatMineDH project. Others are involved as follower cities or just participating to this occasion because of their interest and their kindness. So with this, I would just let you go ahead and then jump into the presentations. Thank you a lot, Emilia.
Thank you. So first, to place us in general context, some of you are Polish and are very familiar with the situation, but many of us are not. So we have the pleasure of having, and the honor of having, George, who is engineer, economist, and specialist in renewable energy, who founded in 2001 the Renewable Energy Institute. He's a director of postgrad studies in renewable energy for business, a member of the Presidium for Energy and Climate Policy Committee and the Polish Chamber of Commerce, and member of the district heating transformation team at the Ministry of Climate and Environment. So George, please put us a little bit in the context of what's the situation in Poland right now for the district heating, a little bit of the history and the challenges in general that are facing before we dig into our follower city, one of your case studies, our follower city, and the HeatMine case studies. The floor is yours.
Thank you, Emilia, for this kind introduction, and thank you for the consortium of the project to inviting me for this short presentation. And I'm happy that you are going to focus on Polish district heating today. I prepared some slides, and really I would like to focus on decarbonization and electrification. As you know, regarding decarbonization, we have a lot to do in Poland. I would say we have a big potential to reduce the CO2 emission from heating and from district heating, and the electrification is one of the solution. But I would like to start from the general overview of the institutional structure. Of course, for us, the most important are the district heating companies, but they are operating in a specific institutional environment. So last year in Poland, it was a small revolution within the governmental structure, because till the June last year, the energy, the heating and renewable energy and regulation belongs to the one ministry, Ministry of Climate and Energy, and since July, the new ministry was established, Ministry of Energy. So the Ministry of Energy is now responsible for the heating and for district heating and for energy regulations. And the Ministry of Climate is responsible for renewable energy. Ministry of Climate and Environment is also a supervisory organization for the biggest fund for environmental protection in Poland. It is the biggest fund in Europe for at the national level for supporting energy transition. And this fund is very important also for the district heating sector. The case study which will be presented, the Końskie, also is a beneficiary of this fund. And under the Prime Minister, there is an independent energy regulator. The regulator is issuing concessions and approve the tariff for the district heating companies. So we are sharing the group of the district heating companies for two. One are the concessionate district heating companies. There are more than 400 such companies, and about, let's say, 1,000 of local heating system, and they apply every year for the regulator for tariffs. But we have also more than 10,000 local systems smaller than 5 megawatts, including 5,000 local heating systems 1 to 5 megawatts. And they are in a, let's say, in a big, they are approaching a big challenge, because first of all, they are waiting for the ETS2, the emission trading system. So this is a kind of a headache for the Polish smaller district heating system. And we have two big district heating organizations, the Polish Chamber of District Heating and the Polish Thermal Energy Association. The first one is mostly focusing on the, let's say, local communities and the smaller district heating systems, and the second one is covering mainly the big energy companies. So this is the overview. And when we are going to the details, so you can see the red or the orange line. This is there is the distribution of the number of the companies, district heating companies, among these 400 district heating companies. So we have about 300 companies with the capacity up to 75 megawatts, and we are calling for them county district heating companies. And we have about 100 very big companies, including, let's say, Warsaw district heating system, more than 2 gigawatts. So this is not, let's say, the district heating companies are not so similar, because they are operating in different local conditions. They have the different capacities and the different fuel mix. And as you know, Poland is dominated Polish energy sector, including power, and the heat is dominated by coal. And since a few years, the district heating system is more dominated by coal even than the power system. So we have a lot to do regarding decarbonization. 75% this is coal, 15% gas, biomass almost 15%, it is growing. And unfortunately, we have only 0.3% of the renewable energy sources like geothermal, solar, or let's say green power to heat. So this is something we should focus on in our strategy. And regarding the prices, the heat prices. So you can have the evolution of the prices of the district heating. This is the cost of the heat, no distribution. And as you can see, there was a shock in the years 2001, 2023 regarding the cost of the heat from the gas, also from coal, a little bit less from biomass. But what happened last year, the cost of the electricity, the cost at the electricity stock exchange is almost higher than the cost of lower than the cost of the heat. So there is the room, the potential for electrification, for power to heat solutions. And regarding the future, so we have almost approved finally the National Climate and Energy Action Plan. It is one of the latest plan approved in the EU, because it was not so easy to agree the energy transformation speed and the pace and the structure of the fuels. So there is the fuel mix for the district heating in Poland 2025. As you can see, we are going to give up coal after 2035, before 2030. We are trying to use even more gas than today in the years 2030, 2035, more biomass than today. But the most important for me is the top of the bars. I mean the heat pumps or the electric boilers. So we would like to increase very fast the share of the electrification in the coming 10 years. And in the National Climate and Energy Plan, there is a lot of about electrification. So the government agreed to set up the preferential conditions for the developing of the heating system using renewable energy, but especially to integrate weather-dependent renewable energy in the heating systems. And the development of the storage, heat storage systems was emphasized, especially seasonal storage. And the government would like to start quite interesting actions regarding the development of the market of domestic technologies. We mean European. So this is a lot of about local content, and the government realized that we are very dependent, technologically dependent from on China's supply of the let's say photovoltaics or batteries, that we have the opportunity to develop European technologies in the case of the power to heat. And of course, we would like to focus on the heat pump and the heat storage. The electric boilers, as more flexible than heat pumps, are more and more popular. And for smooth sector capping for electrification, the dynamic tariffs are promoted. And last but not least, National Fund for Environmental Protection, this biggest fund, will prepare additional measures to support integration of the heating system with the power system. Our power system is not also flexible enough because we had a lot of coal, And for today, already free program for supporting energy, thermal energy storage and electrification are open for the let's say district heating companies. So to summarize this plan, the governmental plan, we are going to reduce the share of the fossil fuels, and we would like to stop the coal after 2035, and the rest it will be the gas. And we are going to increase the green part, and especially we are going to achieve in 2040 16% of electrification and of the district heating system, and it should be especially the clean power, clean renewable energy power, and converter power to heat, supported by the different type of energy storage. So in the National and Energy Action Plan, there is a roadmap for the capacity of the heat storage. I translated this for the number of companies which could install the average thermal storage system up till 2030. So in 2020, it was only 6 tank thermal energy storages installed. Now it is 8, and several is under construction. So it seems that the government would like to have that each to achieve at least 1 thermal energy storage system in each district heating company up to 2035. And just to take to something away, I would like to inform about 2 reports. Unfortunately, they are available in English. First, it was prepared by our institute in the cooperation with the district heating companies. This is the green electrification of heating. You can upload of heating system. You can upload this. There are also some provisions regarding regulations, and the roadmap for heat storage in Poland. So if the presentation will be shared, you can upload, and I can give you more information if you wish. So thank you for listening. If there are any questions, I would try to answer now or at the end of the workshop.
Thank you. The flexible heat pump with heat storage and intelligent electricity purchasing. Konrad, thank you for being with us today. You are the R&D director at IEO. Please, the floor is yours.
Sure. I'll try to share my screen. Okay, can you see the presentation?
Yes, and it's in the right mode as well. Perfect.
Okay, great. So yes, I would like to say a few words about the transformation of the district heating system in Szczecińska city in Poland using heat pump and seasonal thermal energy storage. And at the beginning, I would like to say a few words about this system. So here you have some summary. So the installed capacity is above 20 megawatts thermal energy, the thermal power, but it operates on a daily basis below this threshold, so below 15 megawatts. And the overall heat production during the year is approximately 30 gigawatt hours with 160 almost 160 customers of the company. The main so it is also the most, let's say, common size of district heating in Poland, and the main source of heat is coal right now, operating on the coal boiler. And in the recent years, there was also an addition of 3 gas boilers that started to exchange the heat sources they exchange the coal from the heat sources. And there is one distinctive feature about this company. It's not only provide the heat, the district heating, but it is also the local distribution system operator, which means that it has concession for electricity trading and concession for electricity distribution. And so the company basically tried to get the best of combine these two works together and have the best economical outcome for their system. And that is also why the idea of the power to heat technology is also a kind of natural in this in this setup. Maybe one thing that I should mention is that the system was designed for higher temperature. I mean, above 100 Celsius degrees, but it operates on the lower temperatures, mostly between 70 and 90% on the supply stream of the network. So it is important when we will talk about the heat pumps that we need to get to this 70-75 Celsius degrees. So this is one of the problem. But yeah, we try to size this new system with heat pump, and our goal was to achieve more than 50% of the heat demand from heat pump. And we calculated, let's say, we sized this heat pump to 3.5 megawatt thermal power, with average COP approximately 2.6, so it's also lower than COP that you can see on the residential side. And we connected because of the higher temperature of the system, and we connected this heat pump to seasonal thermal energy storage with, let's say, approximately 2 gigawatt hours of thermal capacity and the volume approximately 40,000 meters squared. There are probably 3 reasons why we choose seasonal thermal energy storage, or to technology pit thermal energy storage, not the tank thermal energy storage. First is that we needed, let's say, higher thermal capacity, so several thousand square meters in the storage, and in that region, the pit thermal energy storage is just cheaper. The second reason is that the company have a place for it, had a plot for this kind of big installation. And probably the third reason is that when we look at to the future, and we would like to, so the next step of the transformation in Końskie would be to add solar thermal collectors on photovoltaics field, and that will even increase the thermal capacity that we will need in the system. So this is the setup, let's say, of how it will be built. So at below you have the main boiler room, and on the north, 200 to 250 meters above, there will be the where the storage will be built, alongside with heat pumps and farms for these heat pumps. So so this is how it should look like in the future. And the principle of operation, I think, is straightforward. So in the summer, we would like to store as much as cheap heat connected to the low electricity prices during the summer. We'll also have some transition months, so October and April, when the storage will also help to stabilize the coal boiler, because there is a decrease in efficiency when when we are in this transition season. And in the winter, of course, the storage will be discharged and the heat pump will continue to operate. So maybe the next slide will show how the system will work. So you have now the demand for heat power during the year. And as you probably can see, the most demanding part is the summer, when the heat demand is very, very low, and we have, let's say, the excess of the heat power from heat pump. And this region, it will operate sometimes only for 1 hour or 2 hours a day. So it was kind of technological question that it is even possible for this kind of big installation to work, to switch on and off that fast. But it looks like it can happen. Of course, right now we are switching to 15 minutes, so it will be even more demanding. But the analysis is on 1 hour resolution. And below you have the state of charge of the storage. As you can see, the peak is somewhere into the September, and after this month it is very let's say dynamic decrease of the state of charge of the storage. And here you have the ordered plot of the heat power in the system. So as you can imagine, the most heat power is needed in cold temperatures in the winter, and on the right you have the let's say the summer setup. And this time in green, you have the heat pump operation. You can also see the decreased in the performance coefficients near to the winter. So when it's cold, of course, the coefficients will be lower. And in the summer, the storage is the main source of heat. As you can see, there is not the continuous let's say performance of heat pump, but it is chopped by 300 cycles per year. You will have also like approximately 50 short-term cycles, so it is on off states shorter than 3 hours, and of course this is main reason for the cycles are the costs of the prices of electricity that we look at, and we try to optimize system for them. So this is the view of the cost optimization of the system. So the main idea here is that the cost of heat produced from coal will be increased in the next years due to the emission trading system ETS2, and because of that we will see also the gradually increasing savings of the system. So we'll start with, let's say, so this is in Polish zloty, but more or less if you divide it by 4 it will be in euro. So we'll start with 150,000-200,000 euros savings in 2030, and in 2030 it will be 1 million euro of savings for virtual savings for the system, so for the company. And because of this increase in the cost of coal heat, it will be also more profitable to switch the heat pump more often, and we will so after, let's say, after 2030, it will be about two-thirds of the whole heat demand will be produced by heat pump, and let's say 8 to 10% will be taken from the heat storage. So the overall cost of the system is approximately 10,000 euros. As you can see, the economical parameters is not very high, but still it helps the company to achieve their green goals. and this is calculated including the 4 million euros subsidies from Recovery and Resilience Plan. So we need this subsidy to make this investment happen. And this is the summary of my presentation. You can just, if someone wanted a reminder, but this is the end of my time, I think. So thank you very much.
Thank you for sticking to the time. We have a lot of speakers, but we wanted to make this efficient. And as mentioned, the presentations will be available online, and I'm sure people can contact you for more information. Are there any questions for Conrad? If not, I have one quick question for you. What is the temperature for it's pit thermal energy storage, right?
Yes, it's pit thermal energy storage. So the temperature of it's the highest temperature. Sometimes because it helps also with coal boiler. The top is near to 90%, but it mostly operates on below like 75 Celsius degrees, because this is the top level of heat from heat pump.
Thank you. They worked with 2 cities to do their case studies in Poland, so Barlinek and Szczecin. I apologize for my pronunciation. However, Zgierz decided to be one of our follower cities and learn as the project progressed from the lessons learned, best practices. And here today we have the pleasure of having Damian Greba. You are R&D project manager at PGE Heat Energy since 2023, and you have a 7-year experience before that in CHP plant as a technical and operational staff. So you know all the technicalities and technicities behind the production. Damian, would you like to share your screen and tell us a little bit about the district heating network in Zgierz?
Yes, of course. Thank you. Hi, everyone, again. I'm sharing my screen, yeah? My presentation.
Yes, great. Perfect.
Yes, okay. Hi, everyone, again, and thank you, Emilia, for introduction me and for opportunity to take part in this project, where we could join few interesting webinars and meetings. And as you said, today I will shortly present CHP plant in Zgierz, actually the transformation of PGE Heat Energy CHP plant located there. And first, let me describe in general PGE Heat Energy. We are the largest producer of electricity and the district heating in Poland. Last year, we have produced over 7 terawatt hours of electricity and over 45 petajoules of heat. And we are operating in 15 locations in Poland. And one of these locations is CHP plant in Zgierz. Originally, the plant was commissioned almost 60 years ago, and as a plant where dyes were produced and was fuel powered with carbon in the form of lignite. And over the last 40 years, its main business activity is producing heat and energy. And PGE Capital Group is maintaining the plant since 2010, so it's over 15 years now. And nowadays, the plant is the main producer and the distributor of heat for the city, with a district heating system length of over 50 kilometers. And before 2022, the decision to transform the plant in direction of completely phase out of lignite was made. And the the construction and installation lasted between September 2022 and October 2023, and it included installation of 3 gas engines as a cogeneration units, peak load boiler, which now cooperates with existing peak load boilers, and a small solar collector system. This led to the commissioning of lignite fire boiler and 2 turbines that was technologically linked to it. Later on, we measured the effects of modernization, and it resulted in significant reduction of emission, such as almost 100 reduction of CO2 and particulate matter emissions, and over 50% reduction of CO2 emission. And actually heading towards to the end about this investment, we can also consider 11,000 of avoided truck runs for transportation of lignite and ash, what results in almost 500,000 liters of unburned fuel for those trucks and over 120 tons of avoided CO2 emission. So that's the additional effect. And that was a lightning fast presentation of this investment, but I would also like to mention two other initiatives that PGE PGE Heat Energy has developed in Zgierz and in our other locations. The first one is hybrid heat substation. That's how we called it. Where in existing dual function heat substation located in a small multifamily building, we have installed a 15 kilowatt air-to-water heat pump supported by thermal energy storage and photovoltaic installation. And, and the effect is a hybrid heat substation which can deliver heat from district heating network or heat pump, and it can be done individually by one of these sources or simultaneously depending on external conditions and automated decisions such as external temperature and etc. As in a heat pump. And the specific installation was handed over in November 2023, and results for 1 year operation are presented here. As you can see, almost 40% of all heat was supplied from heat pump, so the rest 60% was from district heating network, and 25% of all heat was delivered from renewable energy sources. So we mean the heat pump and when it was taking electricity from the photovoltaic. And also 16 tons of CO2 emission were avoided because of reduced fuel consumption in the CHP plant. And those are results for one heat substation. So considering that PGE Heat Energy maintains over 5,000 of heat substation, it looks promising, and we are developing these initiatives. And the second initiative was a digital model of district heating network in Zgierz and other our locations. We used a dedicated software and created a thermal hydraulic model, and now it let us proceed multivariant technical analysis of modifications in district heating network, such as, for example, changing operation temperature, connecting new heat sources, or integration additional distributed heat sources such as hybrid heat substation, as I mentioned above. And we are still developing those initiatives. For today, it is all I have prepared. So thank you for your attention. And Emilia, as you said, we have a lot of people who want to say something more, so I give you the voice again.
Thank you very much, Amy, for that presentation. And the purpose was for you to say is we're looking at certain solutions, but I hope that the listeners can also pick sort of best practices and lessons learned from you guys. In this hybrid station, it looks like it's been very successful. Do you plan on replicating it and installing it in different plants across Poland, since it's been so successful?
Yeah, actually, yes. We've seen it very promising because there's a few reasons about because of, for example, it's the way of electrification, yes, of district heating. It also includes distributed heat sources, so we are talking about fewer heat losses. and it of course increases the security of heat supply because we have two sources in heat substation. And as other people said, Mr. Grzegorz and Mr. Konrad, we can cooperate with energy prices, so it lets us optimize the process. So yeah, so yeah, we see it as a promising way of developing.
Excellent. Thank you. Marco, you have a question?
Thank you. Yeah, I was curious, what is the ownership structure of these hybrid substations? Does PGE also own, I don't know, the entire system, including the storage and maybe even the photovoltaic system, or how is it?
You're asking about the other components, yeah, of this heat substation.
Yeah, exactly.
Yeah, so it was a 15 kilowatt heat pump, and also it was 0.8 square meters thermal storage, and it was the biggest one we could avoid in this room. And it's too small, but we couldn't do it bigger. And also it was a photovoltaic installation of power, almost 6 kilowatt peak power. And we didn't want to cover all the heat demand. It was a research R&D project, so and it was 2 years ago, so it didn't so obvious that it will be a good installation to operate. So we did it as a compromise, and we tried to cover more or less 50% of heat demand, and it stopped at 40 in 1 year. So it's quite what we expected.
Mm-hmm. And you are the owner of these systems, so do you need special agreements? So you are the ones installing also the photovoltaic, for example. I'm wondering about any need of agreements with the customers.
Yes, the installation is all our. So yes, we have to have agreement of the people that live here, and honestly, they were very happy to do this, so they didn't make any problems. We asked them later if there was such any problem or noise or something like this, but the answer was that no, that everything was okay. So this time, I'm not sure if always it will go so easy, but this time they cooperated very much.
Thank you.
Excellent. Thank you very much. So now we've had a good general introduction of the situation in Poland, 2 different cases. For the second half of the knowledge exchange forum, let's focus on the HeatMineDH case studies that we've worked on, analyzed, planned. For the past 3 years, the HeatMineDH team has worked very, very closely with Lily Wolny and your team with the 2 cases of Barlinek and Szczecin. So Lily, can you please, let's start with Barlinek. Could you give us a quick introduction of what the system looks like and how it's set up?
Yes, of course. Just a second.
And maybe while you start sharing, you are the manager of funding and innovation at SEC.
Yes, exactly. I'm in charge of the department that is responsible for innovation, for introducing new technologies to our company, and we also search for external funding for that. So both on national level and in National Fund for Environment that was already mentioned today, and also in the on the European level, like in CINEA, for example. Am I sharing my screen?
Yeah, and we can see it in presentation mode. It's great, as it should be.
So perfect. So yes, hello everyone. As you already know, my name is Lili Wolny. I work for SEC. That is the abbreviation of Szczecińska Energetyka Cieplna, or District Heating Company of Szczecin. We work with both production and distribution of district heating. And before we go to Barlinek, I will present you the share structure of our company, because SET is actually a group of companies owned by E.ON Energy Infrastructure Solutions Polska. And under SET, with our main headquarters in Szczecin, we have a number of different smaller companies. And one of these companies is SET Region. That's the company that owns smaller systems in a bunch of locations located all over the northwest Poland. And one of these locations is Barlinek. For the past few years, SET has been preparing the big initiative called Coal Exit. So we are preparing for the decarbonization of all of the systems that you can see in the presentation. So it is a big challenge for us, and that's why we are searching for opportunities like HeatMine to get an external view on what we could do in these systems, because they are quite similar, even though they have different local conditions, but all of them are based on coal, and they are all high temperature district heating systems. In case of Barlinek, we own the network and we own the heat sources. There are two heat sources. One of them is heat plant consisting of 2 coal boilers, and the other one is the CHP installation. It's owned by SET Energia, again a company from our capital group. So it's we all have the same owner that owns everything. So we have installed capacity of almost 15 megawatts. We have almost 17 kilometers of network with supply temperature in winter on 95 degrees Celsius. Yes, so that's how it looks like. You can see the map, so you can see how I mean, not complicated, but it's quite a big challenge for us to distribute heat from here. You can, I don't know if you can see my cursor, but on the top side of the map, there is our heat plant, and it has to distribute heat to all the city of Barlinek. So that's quite a big challenge for us. And as I said, we've been trying to find a solution for all of the systems that we own. And yes, I guess I will give floor to Ralph, so he can tell a little bit more about the answers they have for us regarding the system.
Wonderful, thank you. I don't know, Emilia, if you want to have a Q&A session in between, or just should we keep on?
I'm thinking you guys can continue, and so we can take the whole Barlinek case, the case and the analysis at the end.
Perfect, wonderful.
We're also running a little late, so.
Oh, okay. So let's go direct into it. So yeah, Anna is sharing her screen. If you go for presentation mode, exactly. So within the HeatMineDH project, our task was to look at possible decarbonization pathways for the Barlinek case, and we actually also were looking a bit into economic risks on uncertainties we have in the future. Next slide, please. So the overall methodology we used within the HeatMine project was starting first with a heat source mapping that has been done for all HeatMineDH cases. I will give a bit of an insight into the HeatMineDH Explorer we developed for this purpose, where we looked at different waste heat and heat, ambient and renewable heat sources and potentials. And then specific for Barlinek, we did a so-called pathway optimization. So we not only looked at 1 year, but we looked at the overall time horizon starting at 2035. That's like the first year where decisions are realistic, basically. 2040, 2045, and 2050, considering the existing units and a couple of restrictions for the future. For example, we're assuming that there's not so much biomass, but we will go into those things a bit later. You looked at various scenarios, reference case, a so-called temperature reduction case. That's the both we are going to present today. Looked at also seasonal storages, CO2 prices, electricity prices, but in terms of timing, we're going to focus today on the reference case and the temperature reduction case. And finally, as I said, we're looking into uncertainties of the future in terms of uncertainties in electricity prices, biomass prices, biomethane prices, and the Monte Carlo simulation has been done. Go next slide, please. Exactly, the HeatMineDH Explorer. Just very briefly, I would like to share now my screen. I hope that works so well. I hope you can see my screen already. Is it possible to know? No, you cannot see my
Actually not.
I need to go on sharing. Okay. I hope you can see my screen now. Exactly. So that's HeatMind. It's an interactive web tool that is free for everyone to show. So that's the reason I'm not showing a PowerPoint, but I'm really showing the real tool that's online available. Actually, that is the documentation we set up for the HeatMineDH Explorer, where you can see all this methodological background, how we looked at sewage, waste heat from sewage, from industry, from solar thermal, geothermal, and from a previous project, we also had an economic evaluation, but that's not really used in HeatMineDH. So there's the documentation, and there's the actual GIS tool that has all these cities, not only from the HeatMineDH case studies, but also from some other case studies included. And we decided to show that too because it's interactive, and you can really look into the data and look into the things we identified. Although I have a small disclaimer, some of the data are still under discussion, or not really under discussion, but under refinement, let's say, and they are not all data points that get included in the HeatMine in the Explorer. I just noticed when starting to look into this thing, just for example, if you for example, like looking for Szczecin, for example, if you go to the region, it might take a while, so I opened it in another tab. No, here it is. Here we are. So here we have, for example, the assessment for Szczecin, where you have industrial waste. It is unfortunately not yet shown, but you see just clicking through this. For example, you see the possible sewage wastewater treatment plants. There has been assessment of shallow geothermal energy done. So you see, for example, here an area where some assessment has been done of potential energy that can be used from shallow geothermal. A similar assessment is also related to the open areas on solar thermal. There is some assessment on sewage potential, not coming from the sewage treatment plant, but coming from the sewage channels. So that is an estimation where these two sewage channels are, and what location you can maybe generate some waste heat or generate some heat out of these sewage channels. As I said, unfortunately, the others are not introduced. But if you go, for example, for Brunswick in Germany, I believe there is some examples how the waste heat, how the industrial waste heat looks like. So you can look at those, and you can see here, for example, a waste heat potential already identified for the city of Brunswick. As again, sorry, the data is not yet 100% ready, but we still have a couple of months to run with the HeatMineDH project, so we will refine those data. And now returning to Anna's presentation, I will hand over for her to show the rest of the project, or basically it's a main work what Anna did on the pathway optimization. So please, Anna.
So as Ralf already said, we did a pathway optimization for the Barlinek use case, and in this pathway optimization, we not only looked into the investments between 2035 till 2050, but we also incorporated the currently supply of the network, which is 100% fossil fuel with 2 coal boilers and a natural gas CHP, and we also incorporated the fixed investment plans for 2030, which are a biomass and a multi-fuel heat-only boiler. For the investment decisions, we chose heat pumps, which are either sourced by air or by the sewage water from the wastewater treatment plant. Then we had an electric or a biomass heat-only boiler as an option, a gas CHP, and a short and long-term heat storage. For the reference case, which results we show later, only the short-term heat storage was an option. A short overview of our price assumptions. For the electricity prices, we used hourly values, which decrease between 2035 and 2050, while the peaks rise. For biomass, biomethane, and waste heat, coal and natural gas, we used fixed prices in euros per megawatt hour, and we also added additional taxes and fees for electricity and natural gas. These divided into fixed value and variable values. For coal and natural gas, we also added CO2 prices, which start at around 120 euros per ton CO2 in 2035 and rise up to 150 euros per ton in 2050, and these influence significantly the prices for coal and natural gas. It's very important to assume these CO2 prices because the EU ETS2 will start in 2028, and this is a market-based carbon price on fossil fuels, which also affects the heating sector, and this will influence the gas, oil, and coal prices. For Poland, the consumer prices will rise by about 17 and 19% for gas and heating oil, and significantly for coal with around 42%. Because Poland has a high focus on coal heat supply, the number of households that are strongly affected by the ETS2 are very high, as you can see here in these two graphs. So the typical Polish household would be affected by an increase of around 500 euros per year of heating cost increase. For our results, these are the results of the reference case. On the left side, you can see the new installed investments, and on the right side, the heat production. You can see that there are two investments in air source heat pumps in 2035 and 2045 with around 3 megawatt capacity. The existing biomass boiler will be replaced in 2050, and there's also an investment in the water heat pump with the wastewater treatment plant as a source. For the heat production, you can see that the biomass was limited. I didn't explain it in the slide before, so we included a biomass limitation of 50% in 2035, which decreases to 25% in 2050. So this is what you can see here, while the share of heat from the air source heat pumps will increase over time. And we also have some shares of natural gas between 2035 and 2045. There's also an investment in a short-term heat storage in 2035 with around 180 megawatt hours. And the existing coal boiler, which could be operated till 2045, is not operating in this optimal scenario. Here you can see the hourly heat production for the 4 support years we looked at, and you can see that the share of heat pumps will increase. In the first 2 years, the peaks are covered by the storage and by natural gas, while in the last year, 2050, the peaks will be covered by the biomass boiler. When we look deeper into 2035, we can see how the air source heat pump operates. So the efficiency increases in the summer where temperatures are higher. And you can also see that here the peaks are covered by the storage system. The second case we looked into is the temperature reduction case. So we used the investment decisions of the reference case and reduced the supply and return temperatures by 5 Kelvin and by 10 Kelvin. So you can see here the supply temperature and the return temperature in versus the outside temperature, and we reduce these peaks, the minimum supply and return temperature stays the same. This has two effects. One on the network losses, this decrease up to 3%. And the second effect is the increase in heat pump efficiencies. The COP of the heat pumps will increase up to 11%. You can see it here, especially in the minimum COPs. In the winter months, we have an increase in the COP for the air heat pump and also for the wastewater treatment plant heat pump. This also affects the levelized cost of heat in euros per megawatt hour. So here you can see the LCOH for the base temperature in turquoise green color. The LCOH is expected to decrease over the years, and the temperature reduction also decreases the LCOH by an average of €1.14 for the 5K reduction and €1.97 for the 10K reduction. And this has a great effect. So it's around €24,000 per year for 5K reduction and €42,000 per year for a 10K reduction. And this, if you calculate it over the 20 years, it has a great effect in energy, in cost savings. So these were our results. And now I give over to Ralf to conclude our.
Yeah. So there's many other results, but for timing reasons, we're just showing those. But what we can see, and there are, in our point of view, two, we call it no regret decisions. That makes sense in any case for reaching these energy efficiency directive targets 2030 to 2050. So the first one is the heat pump. Our first reference here is 2035. I guess if we would have done it for 2030, maybe that would pop up also, and we haven't done it. But it's at least latest for 2035. It is economic. We also tested one scenario with huge electricity prices, but then it came later. The heat pump came later with the high electricity price scenario, but there still was one. And for the standard electricity price scenarios, air seems to be the most economic heat source. I saw in the chat some discussions about air source heat pumps. I'm happy to discuss further on that one. The second no regret decision I see is storage. And we had at minimum 107 megawatt hour capacity storage. In many cases, we had much higher, like 180 megawatt hour capacity storages. And they most often already invested in 2035, our first year. So both heat pumps and storages seems to be no regret decision for the Barlinek district heating network, and I believe for many others as well. Second main conclusion we had that it is important to consider the CO2 prices, although our assumptions are no one knows what the ETS2 price is going to be. We assumed a price is similar to the World Energy Outlook scenarios. We also actually tested scenarios with lower CO2 prices. Obviously, more fossil fuels are used, but still investment into heat pumps are the most economic solutions in 2040 then, or starting from 2040. And coming to the last conclusion for this specific session, when we look at these scenarios with reduced supply and return temperatures, at least there's if you look at it from just a 1 year basis, it's not that high. But if you accumulate these savings over a longer period, because you need to invest money to be able to reduce the system temperatures. So looking at these numbers, if you are able to invest €500,000 into the buildings, into optimizing the building heating systems, and if you're able to reduce your peak supply temperature by 5 degrees, and return temperature at the same time, you will be able to save €500,000. So that then you are then your investment has been matched. So that's our main conclusion for this session at the moment. And we're happy to discuss any of those.
Thank you. I just need to unmute myself. Thank you, Ralph. And then I'm sort of switching things around. You just presented, but now I'm going to present you guys so people have an idea who was just they listen to. Anna, you have been working at AIT since 2020 and are currently employed as a technician in competence unit integrated energy systems, where you are working at a field energy scenarios and system planning. You hold a bachelor degree in industrial energy technology from Montanum University, Leuven. And you're completing your master's degree in the same field, and this is part of the results of the studies you've done, right? Under Ralph, I don't know if you need an introduction, but I will go ahead anyway. You are a senior research engineer and is working at AIT since 2009, where you're leading a team of 4 people in the field of district heating and integrated energy systems. The focus of the work is development of decarbonization pathways and sustainable districts. You have a key position in international networks like the IEA Technology Collaboration Program on District Heating and Cooling. Are you the EXCO representative there for Austria?
I'm the alternate EXCO representative for Austria.
And then European Technology Innovation Platform for Renewable Heating and Cooling. So RHC-ETIP, which many of people here know.
Yes, we would actually welcome Polish members as well, so that could be very interesting. Or do interesting stuff in Poland. So the IEA would welcome very much the Polish ministry to join. But that's maybe on another plate.
But let's continue on that one and see what possible collaboration possibly come up at the end of the discussion. So thank you. There has been a great chat and a lot of bubbling in the chat, so I will not go over this, but I would like to open the opportunity if anybody has questions for Anna and Ralph about the work they have done. This is a good, if you need any clarifications on the presentation.
I just read in the chat one comment. The biggest efficiency gain with the heat pump is not in reduced forward temperatures, but the return temperatures. We did both. So we assumed that heat demand more or less stayed the same. So we reduced the same amount, the supply temperature, the return temperature has been reduced, or a similar amount has the supply temperature reduced to stay on hydraulic balanced levels. We're assuming both going to be reduced at the same time. So we do not assume that new consumers will be connected. In this specific case, it is both reduced at the same time.
Great. Thank you. Then you're doing my job. Having said that, let's now look at the last but not least case of Szczecin. So also, Lily, would you like to give us a quick presentation, and then after Lily and Marco, you can take over directly. And I'll take this opportunity to introduce Marco really quickly. Marco, I don't think you need a presentation either, but those of you who for some reason do not know who you are, you're a senior researcher at EURAC Research in Italy. You're involved in various European research projects focused on sustainable heating and cooling applications, especially in the district heating sector. You're the coordinator of the HeatMineDH project, and other projects' interests include energy efficiency in industry, solar thermal energy, energy scenario design, and optimization. So it's a really quick introduction, Marco. Having said that, Lily, Marco, please let us know what work has been done in Szczecin.
Okay, so again, I will start with sharing my screen and then I will give floor back to Marco. So you already know a little bit about SET as a company, and the largest system in our portfolio is located in Szczecin. That's also where our headquarters are located. And just to give you some numbers, we have 5 heat sources in our system. We have almost 400 kilometers of district heating grid. We have over 20,000 clients, and we have installed capacity, our own capacity of 180 megawatts. To give you a short overview, the Szczecin is divided in half by Odra River. And so we had to connect 2 sides of the river, the left and the right part, and you can see the structure of the system. So we have our own district heating sources, which are located all over the place, with our biggest source located on the right side of the river. It's Dąbska heat plant. It's based on coal right now. And of course, it's part of the coal exit initiative I mentioned earlier. So right now we are thinking about the decarbonization of it. Other heat sources that we use in our system belong to the municipality of Szczecin. That's the waste incineration plant located between the two sides of the Odra River. And we also have two external sources that belong to PGE. One is coal-based, the other one is biomass-based. And between all of those players in the district heating market, we have to find a way to keep our system efficient in the future. So, of course, we are working on our own sources. And yeah, we are thinking about how we could decarbonize such a large system because it's not so easy. Szczecin again is a high temperature system.
You froze for a minute there.
Sorry, what was the last thing you heard?
It was about the coal plant.
Personally, I was able to hear everything. I don't know how many people had this issue.
Yes, me too.
Okay.
All was good from my side.
Okay, never mind. Sorry.
Yeah, okay. So as I said, we are searching for decarbonization possibilities for such a large system, and we are investigating a lot of possibilities, like, for example, wastewater treatment plant, the geothermal sources. And my department is searching for funding possibilities for all of that because those sources are expensive, of course. And yeah, I guess that's it from my side. So you can see what we are dealing with. And yeah, I'm giving voice to Marco.
Thank you very much, Lily. So I'm going to share my screen. I think you should now start seeing my slides. I'm going to switch to presentation mode. Do you see it properly?
Yes.
Thank you. So first of all, this contribution was prepared, of course, in collaboration with SETS, but yeah, it's mainly our estimates at EURAC. I would like to credit my colleague Daniele Nania, who made even most of the technical work, even if I'm presenting today. So the introduction about the network as such was already provided by Lily, so I will be very quick. You see here a bit the distribution of the existing sources along the year. And we have this, let's say, four main sources. Two of them which are just fossil fuels, coal and natural gas. Then we have an important waste to energy plant, currently covering about 16% of the energy, and the biomass, the existing biomass system shown before by Lily. The classification of the waste to energy system is still a bit of subject of debate, so to say. At the moment, the most conservative assumption is not to consider it as a renewable. Classifying the renewable content would require also some additional metering, which can be costly, complex, and so on. So to be more conservative, these very severe constraints about the renewable share were assumed. The overall heat production is more than 1 terawatt-hour per year, so pretty large. And with this important decarbonization need. And you see the current distribution of the sources, how the system is covered along the year in the top left figure. So we started our work screening a bit the potential sources, and just a second, trying to activate the pointer. Okay. Biomass is already being exploited, but it could also be increased. And then the subject of heat pumps was deeply explored. The HeatMineDH project also has as a main target low temperature sources, even though the entire system, of course, needs to be considered. So a wastewater treatment plant was already being considered by SETS, and we did an independent analysis on that to support their work. Then we also explored waste heat opportunities, both at high and low temperature. And finally, we took into consideration into our scenarios also the possibility to use some deep geothermal sources. This is an analysis started by SETS again, but I will mention some limitations there, especially related to the duration of the works, so to say. With these sources, one can already reach a good share. So our main target in the project was in terms of time horizon 2035. So to make the system compliant with the efficient district heating and cooling requirements by that time. So basically reaching 50% of renewability. Other sources could also still be identified, like river heat pumps. There are many water basins around Szczecin, which could also be considered for even further decarbonization. In this slide, I give you a look on the temperatures involved in Szczecin. You see the supply temperature and the return temperature at the top. So it's a relatively high temperature network, even though with a good climatic curve, trying to optimize the temperature along the year. And you see at the bottom the air temperature. So it's, of course, a northern city, so the cold, but without very extreme, let's say, peaks of cold, thanks also to the proximity to, again, water basins and the sea. And you can also see approximate temperature curves for rivers and for the wastewater treatment plant. In particular, I would like to highlight this, let's say, violet curve for the wastewater treatment plant, which is hence a better source, especially in winter, to be coupled with heat pumps to enhance the COP. And focusing a bit on this system, so the power of about 12.4 megawatts was targeted. Even though direct data were not analyzed due to confidentiality, we were able to approximately evaluate the system based on similar cases in other European places, also Europe, also Italy, sorry. Then adjusting the results for the different climate. And in this way, we were able to consider both the temperature of the system, especially targeting the effluent of the wastewater treatment plant and the flow rate. The flow rate can be in general estimated for wastewater treatment plant based on the population size for which the plant is designed. We then did, of course, some assumptions about the temperature difference for the heat extraction, and we also assumed to exploit a certain capacity of the system, so about 80% of the maximum flow rate usage, and in this way, we could reach these estimates about the power. In terms of COP, we did a first conservative analysis, calculating the average COP, combining the temperature of the source in the curve I've shown before, and reaching the supply temperature of the district heating system, so even at slightly more than 100 degrees in certain seasons. This is a conservative assumption because a proper operation of the heat pump could also be limited in some periods or be coupled with other sources to limit the temperature output of the system. So our analysis confirmed basically the initial estimates of SETS, and shown a good potential for this type of source. In the end, for all the sources we have, we convert our numbers into a levelized cost of heat. This was already mentioned by AIT, so I don't want to spend too much time on this, but just to highlight this, that, of course, this contains both an investment part, an investment contribution, and an electricity-related contribution. The electricity-related contribution is strictly linked to the electricity price and the COP the heat pumps for heat pump applications, of course. For the main sources considered here, we estimated the techno-economic parameters, both in terms of size and some investment cost. You see here some figures for possible additional biomass boilers for the wastewater heat pump and also for the deep geothermal plant and the corresponding sizes. Even though the wastewater heat pump is not huge in terms of power, especially with respect to the very big Szczecin network, operating many hours, it can still provide an interesting contribution, so between 5 and 10%, depending on how much you operate. I anticipate that the deep geothermal plant would be favorable in principle for the estimated temperatures it could provide. Still, one of the main issues is really the realization time. So there are certain time constraints to reach these renewability shares and also to exploit funding. Maybe this is an even more stringent constraint, and so it seems very challenging to go for this strategy at the moment. On the right, you see some of the parameters we used also to analyze the investments. So the weighted average cost of capital, the lifetime. This is valid for heat pump plants. Deep geothermal plants could last more, and so the corresponding annuity and some energy prices on the bottom right. So we targeted an electricity price of 140 euros per megawatt hour as an average future estimate. You have seen before that. Of course, in future, prices might fluctuate much more. So we did not perform the big analysis done by AIT for Barlinek. We stayed at a more high level, let's say here. Biomass price, a tentative DH tariff, and also a tentative price for high temperature waste heat. As I mentioned, we identified some waste heat sources, both at high temperature and at low temperature, of course, with very different costs, because the low temperature waste heat needs heat pumps, while the high temperature waste heat does not. But at the same time, the high temperature waste heat typically requires some reward for the source to be negotiated, so to say. So we went for a first scenario including the deep geothermal system. This is economically overall a little bit more favorable, but as I said, not very likely to be realized because of these time constraints. For the new sources intended as the new selected ones, the average levelized cost of heat would be order of 80 euros per megawatt hour with the shares you can see here. So the new sources you can see in the pie chart will provide about a 12.5% from deep geothermal, about 10% from a new biomass, and about 6% from the waste water treatment plant. Overall, the renewable share would be in all cases above 50%, almost 57% if the waste to energy plant could be considered 30% renewable. I mentioned this option because it's the case, for example, for other plants we have seen across Europe. A second scenario we analyzed is instead a scenario without the deep geothermal system, so assuming this will not be achievable, and instead introducing waste heat. Of course, waste heat requires to go for many different sources to achieve a bigger potential. From this point of view, it's more complex probably to manage than a single big plant like deep geothermal, but still has very interesting potential. You see a diagram for the some industrial waste heat sources identified on the left, and a few of them appear to be significantly big. This is an estimate based on general data, based on conversion coefficients, based on the size of the company in terms of number of employees and considering the industrial sector. So it should be verified through their contacts, but still the potential seems very high. Another interesting source of waste heat can be urban waste heat, going to, for example, shopping malls and so on. Here, the potential for Szczecin, however, was estimated to be significantly lower. For sources like this, which are quite distributed in the city, it's also important to include some connection costs. So to keep in mind the distances between these sources and the network. And this we did for the two main industrial sources shown here. So putting overall together, you see a slightly different chart. This is a daily plot of how the load could be covered with different priorities. You now see the deep geothermal plant is not anymore present, but now priority is given first to high temperature waste heat. It's a small contribution. This thin line in green, or this thin green sector in the pie chart. Not a very big contribution, about 3%, but still pretty convenient in terms of economics, because no heat pump is needed. Then a new biomass plant is still introduced, and then some low temperature waste heat, which includes the fraction of waste heat which is below the supply temperature of district heating, but still available at industrial sites. And this is estimated to be a very significant amount. And finally, the wastewater treatment plant is still here, now with a slightly lower share because of different operation and different control of the sources. The rest share is similar to before, even a little bit higher. So this combines a good, let's say, renewability level with an interesting economics. The average levelized cost of heat for this scenario is about 73 euros per megawatt hour. So quite interesting according to the numbers we were able to collect. The different sources individually have very different prices and costs. You see, for example, the high temperature waste heat has here an estimated levelized cost of heat very cheap, about 24 euros per megawatt hour. This relies on an assumption of many operation hours along the year, about 6,000 hours per year. But for big industrial sites, rather continuous operation is typically the case. And for small amounts of heat, it's also very easy to introduce it in the network along all the year. Other sources have much higher costs. You see the individual cost of the wastewater treatment plant heat pump. This is the highest one. In this case, a very high cost for the heat pump was estimated, higher than low temperature waste heat. So there might be some fine tuning of these numbers, but these are the estimates we are able to collect so far. Also, the wastewater treatment plant has a slightly lower number of operation hours, which also affects the final cost. So with this, I would close my presentation and thank you. I didn't include specific conclusions. I think this can maybe discussed directly in the Q&A session and then the final part of the meeting. And thank you again for the attention.
Thank you, Marco, for the presentation. And while people think in case I have direct questions for you, I'd like to read a comment which picks up a little bit on the last thing you mentioned. Here, Raymond mentions that from river or lake, which has a temperature on average 3 to 4 degrees in winter, used as heat source for a heat pump, one can take up about 2 to 3 K. But from sewage water is up to 3 times as much. So it's 6 to 9 degrees. Will this increase the efficiency quite a lot? And I was wondering, and what you said, like in your analysis in that last scenario in slide 11, would you like to comment on this comment, or would you like to react on this comment?
Thank you. You can see here a couple of estimates of COP. Maybe I switch again to presentation mode. You still see my presentation,
yes.
Right? You see, for example, that for the case of wastewater treatment plants, we estimated an average COP of slightly less than 2.5. Again, assuming the heat pump needs to provide the supply temperature for the network up to 100 degrees. For low temperature waste heat, this is better, of course. The source we assume to be around 25-30 degrees along the entire year. It's true, for rivers, it would be significantly smaller. Maybe I go back to the temperature plots I've shown before. So river temperatures typically are more or less in line with the air temperature, but with much less fluctuations and of course without freezing in winter. Still, from a very qualitative point of view, you see the jump, so the lift from these temperatures to the green curve, the supply temperature of the district heating system is quite big in both cases. So it's clear that the wastewater treatment plant has an advantage, and even higher advantage would come from low temperature waste heat. Still, the lift is big. So there is an improvement of maybe 15–20% on the COP, but not more than that. So a bigger impact could be, of course, achieved either lowering the network temperature if feasible, or finding maybe hybrid combinations where the heat pump is coupled to a CHP system and the heat pump doesn't need to provide the supply temperature of the network directly. So I hope I answered more or less the question.
Thank you. I hope so. We'll let Raymond react. Now I'd like to invite you to everybody to turn on the cameras if we start sharing, and let's discuss a little bit. Now we've had these presentations, these cases.